Hi everyone. Hopefully you finished up the district assessment and it went okay for you. If not, please don't worry about it too much. We'll talk about it probably next week. Right now, let's focus on the Pythagorean theorem and we're going to go over sections 7.1 and 7.2 in this lesson. And I'll try to make it not super long here. So we're going to write on the back of our flip chart, so make sure you get that out, and you should have gotten a half sheet from the sub where you can copy down the notes. So flip your flip chart all the way over to the back, the whole entire thing, to where it says Pythagorean theorem / converse. Okay, so we're going to start off with the Pythagorean theorem, which is something that you guys should have talked about last semester, hopefully. So in a right triangle, the two sides that make up the right angle are called the legs. And those are your A and B's. And then the side opposite, the right angle, is the hypotenuse or the C. So the Pythagorean theorem is always A squared plus B squared equals C squared. Now, if you were in my class last semester, you learned about something called the Pythagorean triples. So we are going to write that chart down again. It will be very helpful when we're talking about the Pythagorean theorem and with other problems throughout this whole entire unit. So the Pythagorean triples are basically a series of three numbers that work when you substitute it into the Pythagorean theorem. So you need to have values for each leg of your triangle and then also the hypotenuse. Sorry that this writing is kind of terrible. All right, so the first triple is a 3, 4, 5 triangle. Now you guys don't have to write this part down off to the side, but why this works and why this is a Pythagorean triple is if we take those values and put it into a squared plus b squared equals c squared, if you work it out, you end up seeing that the two sides are equal. Okay? So the next set is a 5, 12, 13. Then we have an 8, 15, 17, 7, 24, 25, and then a 9, 40, 41. There are other Pythagorean triples, but these are usually the ones that you'll see in this class. And then just a side note is that all multiples of triples work as well in the Pythagorean theorem. So all multiples of triples work too. So that means that if I were to take like the triple 3, 4, 5 and multiply those values by 2, that would mean I could have a Pythagorean triple of 6, 8, and 10 that would work in the Pythagorean theorem. So we'll kind of talk about this a little bit on the next slide. So if you are already comfortable with the triples, if you had me, or if your other teacher last semester happened to show you this, you can kind of skip this part of the video. I'm going to go to the next slide that has some examples of how to identify triples, but then I'm going to come back to this slide to write out the whole converse of the Pythagorean theorem. Okay, so again, if you're comfortable with the triples already, you can just fast forward until you see me starting to write about the converse part. So basically, a Pythagorean triple means that, let's say I had a leg of 5 and a leg of 12. If I look at my triple chart right here, look for a leg of 5 and a leg of 12. So if you look right here, we have a leg of 5 and a leg of 12, which means without doing any math, which everybody loves, that missing hypotenuse length would have to be a 13. Okay? If we had a triangle where, let's say we had a leg of 24 and a hypotenuse of 25, and you go to check your triple chart, oh, well, if you look at this one right here, we have a leg of 24 and a hypotenuse of 25, so that means my missing piece must be 7. So it's really just a way to try to make your work a little bit more efficient. Okay? Now, what if we had a triangle where this was 3, and this was 4, would this actually be 5? Now the answer is no. Even though you have the 3 numbers for a Pythagorean triple, they are not placed appropriately. That 5 would have to be the hypotenuse, and it's not. Okay, so this would actually not be a Pythagorean triple, even though it might look like it at first glance. And then finally, let's say we had 16 here, and then 30, and we wanted to find out what the length of the hypotenuse was. Now, at first glance, there is no triple where there is a leg of 16 and a leg of 30. So that's where you want to check the multiples. Do we have a base triple that if we multiplied it by a certain number, we would get 16 and 30, and then we'd be able to find out whatever this missing piece is? And the answer is yes. If we took the 8, 15, 17, and we multiplied it by 2, that would give us 16, 30, 34. So your missing piece would be 34. Okay? If you want more explanation on this, I can help you guys out tomorrow too when I'm back. All right, so back to the flip chart. So the Pythagorean converse is basically a way to determine if you not only have a right triangle, but if you have an acute or an obtuse triangle. Okay? Now, remember, before you can determine what type of triangle you actually have, you need to check to see if you can actually form a triangle from the 3 sides. And in order to form a triangle, remember that the sum of the 2 smaller sides has to be larger than the longest side. Okay, so we're just going to put that in there as a side note. So if we have a squared plus b squared greater than c squared, we have an acute triangle. If a squared plus b squared equals c squared, we have a right triangle. And then if we have a squared plus b squared less than c squared, then that means we have an obtuse triangle. Okay? If I'm going too fast at any time, you guys feel free to pause whenever. I'm just trying to plow through this so that you guys can get to the homework here. But feel free to pause whenever you need to in order to catch up. All right, so let's throw an example here if you guys have space. Let's say we have the sides 4, 6, and 7. Okay, we wanted to know, well, what type of triangle do we have? Well, first check, is the sum of the 2 smaller sides greater than the third? So 4 plus 6 is greater than 7, so we can form a triangle. So then you're just going to substitute into the Pythagorean theorem and just see what the relationship is between a squared plus b squared and then c squared. So this gives us 16 plus 36, and we're going to compare that to 49. Well, 16 plus 36 is 52, so that is greater than 49. So if we look right here, it says if a squared plus b squared is greater than c squared, then we have an acute triangle. Okay, so that's it for the flip chart, but keep it out. And now we're going to actually move on to the little half note sheet. So before we get into working with triangles, we do need to discuss simplifying radicals a little bit further. You should have all at some point last semester been exposed to how to simplify a radical, but it maybe wasn't a huge emphasis at the time. So to simplify a radical, what you want to do is you want to try to break it down using perfect squares. So perfect squares are just numbers that you can square root. So 1, 4, 9, 16, 25, 36, and so on. So if you look at the square root of 72, which of those numbers in blue is 72 divisible by? It's actually divisible by 4 and by 9, so it's your choice what you want to use, but you should try to pick the largest square root possible. So we can rewrite this as 9 times 8. So the square root of 72 is 9 times 8. And if we take the square root of 9, that gives us 3. We cannot take the square root of 8, so we're going to leave that inside the radical. Now from here, you want to check to see if you can break down the 8 even further using one of these perfect squares. And the answer is yes, because 8 is divisible by 4. So we can change 8 into 4 times 2, and then we can take the square root of 4. The square root of 4 is 2, so that's going to go outside. We cannot take the square root of 2, so that's going to stay inside. And then you're just going to multiply what you have outside to give you 6 square root 2. You could have also noticed that the square root of 72 can be broken down into 36 times 2. So you can do it this way as well. And then if you take the square root of 36, you get 6. You cannot take the square root of 2, so you leave it inside. But as you guys can see, you end up getting the same thing. Now for B, we're just going to drop down the 3, but we need to break up the square root of 48. So 48 is divisible by both 4 and 16. Most people probably would pick the 4 first because it's a little bit more obvious. So let's just do that. So 48 becomes 4 times 12. We can take the square root of 4. The square root of 4 is 2, so that's going to come outside the radical with the 3. And then we're going to leave the 12 inside. But then you need to check, can you break down the 12 even further? And you can, because 12 again is divisible by 4. So we're going to take the square root of 12 and turn it into the square root of 4 times 3. We can square root 4, so we're going to drop down our 3 and our 2 that are already on the outside. When we take the square root of 4, that's 2, so we're going to bring that out, and then we cannot square root 3, so we're going to leave that in. And then we just end up multiplying everything on the outside together, and we're left with 12 square root 3. Now, when we're asked to multiply or use an exponent when we're working with radicals, we kind of do this the same way. So when we have 2 root 6 times 3 root 2, all you're going to do is you're going to multiply the outsides together, so that's going to give you 6. And then you're going to multiply the insides together, so that's going to give you 12. So we right now have 6 root 12. But you always want to check to see if you can break down what's underneath the square root. And we can, because you can divide 12 by 4, which is a perfect square. So that's going to turn into 4 times 3. You take the square root of 4, which is 2, and you bring it out. You leave the 3 in because you cannot square root it, and you're left with 12 root 3. Now, for 2 root 5 squared, what I would suggest doing is actually writing it out twice, like this, because that's what it means to square something. And then you just multiply the outsides together, and then you multiply the insides together. And then what is the square root of 25? The square root of 25 is 5, so this is going to turn into just regular 5. And if you multiply by that 4, you get 20. All right, moving on. Okay, so now let's get into actually using the Pythagorean theorem here. So we have the example, find the area of an isosceles triangle with the base 10 and legs of 13. So let's draw an isosceles triangle. It says it has base 10, legs of 13. Now it says to find the area of the triangle. So area of a triangle is 1/2 base times height, or base times height over 2. It's the same thing. We know the length of the base already. That is 10. But we don't know what the height is, so that's what we have to find. So we're going to drop an altitude in this triangle to represent the height. And whenever you drop an altitude, remember an altitude always meets at a 90-degree angle. So we're basically creating a right triangle here off to the side. Okay, so hopefully you guys see that. So now what we're going to do is we're just going to take this right triangle that represents really half of our isosceles triangle. This is our height that we're trying to find. This is 13, and now this portion down here is half the base, so that becomes a 5. Now before you start doing the Pythagorean theorem, check your triple chart, and if you guys check your triple chart, you'll see there is a triple that has a leg of 5 and a hypotenuse of 13, and the missing piece has a value of 12. So without having to do a lot of math, if you use that triple chart, you can fill in the missing piece for your triangle. If you forget the triples, you can always do the Pythagorean theorem and do a squared plus b squared equals c squared. And if you go through and you work this out algebraically and you subtract 25 from both sides, you get h squared equals 144. And if you square root, you get the height being 12. It just, again, if you have the triples down, it just minimizes the amount of work that you need to do. Let me erase some of this. I don't know what that is. Okay, so then back to finding the area. So we've got the 1/2. We substituted in 10 for the length of the base because we want the base of the original triangle. And now we can use 12 for the height. So 1/2 of 10 is 5. 5 times 12 is 60. So 60 units squared. All right, the next one is just a regular Pythagorean theorem problem. So we have a leg of 6, a leg of x, and a hypotenuse of 12. So you should go through and check your chart to see if you have a triple where you have a leg of 6 and a hypotenuse of 12 to see what would that missing piece be. But if you do look at your triple chart, you'll notice that there is not a triple that fits these values. So for this problem, you do have to do the Pythagorean theorem. So we have a squared plus b squared equals c squared. This is 36 plus x squared equals 144. Then we're going to subtract 36 from both sides, and we end up getting x squared equals 108. Yes, 108. And then we square root. So x is going to equal the square root of 108. But again, remember, you want to go through and you want to try to break this down if you can. So what perfect squares can you break 108 up to, or up with, sorry. So 4 can go into 108. So we can write this as 4 times 27, okay? So we can take the square root of 4, which is 2, so that's going to go outside. 27 is going to go in. 27 you can break up using perfect squares as 9 times 3. So you can take the square root of 9, which is 3, so that's going to go on the outside. And then this 3 you cannot take the square root of, so that's going to go on the inside. And then you're just going to multiply the 2 and the 3 together, so this is going to be your final answer for x. So kind of weird, kind of funky. And then our last example just deals with determining if triangles are right, acute, or obtuse. Okay, so always check first to make sure that the sum of the two smaller is greater than third. So 10 plus 12 is greater than 16, so we can form a triangle. So now we're going to do the Pythagorean theorem to see what type of triangle we would actually have. So 100 plus 144, and then 16 squared is 256. And then this gives us 244 compared to 256. So 244 is less than 256. So just look at your flip chart to figure out, well, is a squared plus b squared greater, equal, or less than c squared? And since it's less than, that means that this would form an obtuse triangle. Now for b, again, check to make sure, is the sum of the two smaller greater than the largest? And the answer is no. So this means you cannot even create a triangle. So there's no point in actually trying to determine if it's acute, right, or obtuse. Now for the last one, is 6 plus 7 greater than 4 square root 2? If you weren't sure just by looking at it, you could always substitute 4 square or put 4 square root 2 into your calculator. But since 6 plus 7 is 13, and it's 4 times the square root of 2, you know that 13 is going to be bigger than that. But if you wanted to confirm with your calculator, go ahead and substitute that in. So now let's check a squared plus b squared equals c squared. And I'm going to write the c squared in parentheses just because we are squaring a number with a radical in it. So this is going to give us 36 plus 49. We can come off to the side and work this out. So 4 root 2 squared is really 4 root 2 times 4 root 2. You multiply your outsides, you multiply your insides, and then you break it down. Square root of 4 is equal to 2. So that is going to give us 16 times 2, which is 32. So we use that. Sorry, I should have made that a box. We're going to change 4 root 2 squared to 32. And then 36 plus 49 is 85. And 85 is greater than 32. So since a squared plus b squared is greater than c squared, this would give us an acute triangle. Okay, so that sums it up for the Pythagorean theorem. This is your homework for this evening, and I will be back tomorrow to check this in, so good luck.